Okay ji, Bismillahirrahmanirrahim. Welcome to another lecture of modern control systems. I am your presenter Mohammad Rafiq Ukhtai, Assistant Professor UET Lahore. Let's start with our lecture. So today we will learn another few basic things about the state equations and uh, feedback control systems and characteristics of feedback control systems and Jordan block and some other interesting things. So first of all, let's start with this title. How can we find a transfer function from a state equation? Up till now, you people already know that if you are given with a state equation, then you can easily find its signal flow graph. And from signal flow graph, you can find your transfer function using Mason's rule. So this is the only path that you know up till now. So the question is there any direct path? Is there any direct path by which we move from state equation to transfer function? So shortly we will see and we will check if there is any direct path using which we can, if we are able to find the transfer function of a system using the state equation or state variables or state matrices. So up till now we know that the state equations that we already know are x dot equal to ax plus bu and y equals cx. This is the state equation form that you already you people know. Now if I apply Laplace to these state equations, they give the form s x of s is equal to ax of s only by applying Laplace plus b u of s, and similarly y of s is equal to c x of s. So rearranging this equation A, we can get s minus a into x of s is equal to b u of s. If I write identity matrix Si to make this S a matrix, because A is a matrix and S minus A doesn't make any sense unless and until S is a matrix. So if I multiply this S with an identity matrix, then it becomes Si minus A into X of S is equal to B U of S. Now this Si minus A is of special interest in control systems, in controllability of a systems, in you can say in multiple scenarios in control systems, because this S actually Si minus A inverse actually denotes e raised to the power at in time domain. This is S domain, this is time domain, and these both actually uh, denote state transition matrix. State transition matrix. So basically, state transition. If someone asks you what is a state transition matrix in you can say Laplace domain, you can say that state transition matrix is Si minus A inverse, and the state transition matrix in time domain is actually e raised to the power at. So if I write Si minus A inverse as phi of s, let's just denote this state transition matrix with phi of s, then in the above equation it will become x of s is equal to phi of s b u of s. Now put this in this equation. Put this in B. You will get y of s over u of s is equal to c phi of s into B. Now, if you notice, y of s over u of s is actually output over input. C is the matrix from your state equations. B is the matrix from your state equation, and phi of s can be found from this Si minus A inverse. So if you see, you can find y of s over u of s only with the help of C, B and A. So using only the matrices from the state equations, you can find the transfer function of a system using this equation. Please note that we have assumed the system with initial conditions 0 and matrix D is equal to 0 in this scenario. If we say that matrix D is not 0, and you can say initial conditions are also not 0, then what would be the equations? So for the record I would like you people to note down the following, or you can say the basic equations in time domain as well as in Laplace domain, which includes all the initial conditions as well as all the matrices A, B, C or D. So just for the record, or for your reference, for your ready reference, we already know that time time domain response of a system that we evaluated in our previous lectures was x of t is equal to e raised to the power at. This is state transition matrix into x of 0, which is the initial condition, plus 0 to t e raised to 0 to tau e raised to the power a t minus tau v u of tau d tau. We already know about this equation. This portion we discussed was kind of zero input response, and this portion we discussed was zero state response in time domain. This is zero state response, this is zero input response, and zero input response and zero state response combined can give you the overall system response. Similarly, the y of t, we can write y of t as c e raised to the power at x of 0 plus c integration 0 to tau e raised to the power a t minus tau bu of tau d tau plus du of tau du of, rather I would like to write it as a du of t. So this is the time domain response of a system. In Laplace domain, these equations can be written as x of s is equal to si minus a inverse x of 0 plus b u of s. Now if you see, this x of s was phi of s b u of s. This x of s is phi of s b u of s, but due to initial conditions this factor will appear over here. Similarly, we can write y of s as c into si minus a inverse x of 0 plus b u of s plus d u of s. If your matrix D is not 0 and if you have initial conditions, then y of s has this form. For initial conditions equal to 0 and for D matrix equal to 0, your y of s has this form. C phi of s b into u of s, which is actually C phi of s b into u of s, if this is 0 and this is 0. So if I say that if you are given um, with state equations having matrix A, B, C, and D, you already know that whenever you would like to find the transfer function, initial conditions are obviously 0. So if the matrix D is non-zero, then y of s over u of s would be, transfer function would be C phi of s b plus d. In this way, if matrix D is non-zero, then in this way you can find the transfer function of your system using state equations. Again, the point that you should note is e raised to the power at and si minus a inverse. If I take inverse Laplace of si minus a inverse, this is equal to e raised to the power at. So these two entities, or these two e raised to the power at and si minus a inverse, sorry, a inverse, are of very, you can say, high importance in control systems, because they represent the state transition matrix, and we already have discussed the importance of state transition matrix in control systems. So this is the time domain. These are the time domain equations, time domain response of equation for the time domain response of the system, and then equations for Laplace domain response of a system. These are the standard equations. Now let's move to another topic, which is um, feedback control system characteristics. Up till now, you people already know few what is a feedback control system and what is an open feedback control system is actually a closed loop control system. So up till now, you people know that what is an open loop system and what is a closed loop system. Uh, Open loop system. If I draw an open loop system, it would be like if you have some R of S over here, and then you have G of S over here, and then output Y of S. This is an open loop system. We have an input R of S, it goes to a process G of S, and it generates an output Y of S. So this is a typical example of an open loop system. So for the first characteristic that we will learn about the feedback control system is the effect on error signal. We will see what is the error signal in case of open loop system and what is the error signal in case of closed loop system. Now what is an error signal? Error signal is actually the difference between What is the error signal? The error signal is the difference between the reference output and the actual output. The difference between the reference, or you can say reference signal, versus actual signal, versus actual output. So the difference between the actual output and reference output would give you uh, the error signal. If I say that R of S is your reference signal and Y of S is the output, then the error signal in this case would be Y of S minus R of S, E of S. It would be straight away, for in case of open loop system, it would be straight away Y of S minus R of S. This would be your you can say the error signal, and where Y of S, you can write Y of S as G of S into R of S as well. I can say that we can write R of S, Y of S as G of S into R of S minus R of S is equal to E of S. Taking R of S common, G of S minus 1 is equal to E of S. So this is your error signal in terms of R of S and G of S. This is your error signal in terms of R of S and G of S in an open loop system. Let's call it A. Now, what is a closed loop system? In a closed loop, in an open loop system, you have no control over the error signal. You haven't sensed this error signal. In open loop, if the error is there, it's there. You don't know whether the error is there or not unless and until you sense it. And when you sense it, it automatically becomes a closed loop system. For example, I can say that if I have this process G of S and I have an output Y of S, and there is a feedback loop with a transfer function H of S, and here we have a comparator. This is a reference signal. It goes into the comparator, and from output is also fed back. Let's make it a positive feedback at the moment, or you can say positively, or it would be better if we call it a negative feedback because we are calculating error. So for error, it would be better if we take it as a negative feedback. So this is a feedback loop. Now let's see what's the error signal in this feedback loop. Uh, First of all, let's assume this h of s equal to 1. We can say it is a unity feedback. Then I will come to the point where h of s is not equal to 1. So we have a negative feedback system. We have a reference signal over here. We have an output signal over here. And we have a process G of S, and we have a unity feedback loop, unity feedback path. In this case, our Y of S is equal to G of S into E of S. Y of S is equal to G of S if it is the error signal E of S over here, then I can write Y of S as this E of S multiply with this G of S. What would be the signal over here? Signal over here would be this G of S multiplied with E of S. So I can rather expand this G E of S as R of S minus Y of S, reference signal minus output. This E of S is R of S minus Y of S, where H of S is 0. If H of S, H of S is 1. If H of S wouldn't be equal to 1, it would be R of S minus H of S into Y of S. So G of S is R of S minus Y of S, and then Y of S is equal to G of S into R of S minus G of S into Y of S. Taking Y of S common, Y of S into 1 plus G of S is equal to G of S into R of S. We can write it as Y of S equal to G of S divided by 1 plus G of S into R of S. So from here, if I put this Y of S, if I put this value of Y of S over here, then I can find E of S as expression for the error signal would be equal to G of S over 1 plus, sorry, it would be G of S over 1 plus G of S into R of S. This is the error signal. Sorry, I have to write Y of S over here, so just a second. So if I put the value of Y of S over here, it would be G of S over 1 plus G of S into R of S is equal to G of S into E of S. So E of S would be 1 over 1 plus G of S into R of S. So this is the error signal in case of unity feedback. Now compare it with the error signal of the when there was no feedback loop for the open loop system. Error signal was R of S into G of S minus 1. Here error signal is R of S into 1 over 1 plus GS. So obviously this term, if I am calling it A, I will call it B. So obviously this error signal in equation B is apparently is visually we can see that it would be less than the error of this open loop system, because we have a term 1 plus gs in the denominator, which makes it small. So now we have control over the system. In order to reduce the error, we have to increase this 1 plus g of s term. So if I increase this 1 plus g of s term, I will automatically reduce my error signal. So just by increasing 1 plus g of s, I have control over my error signal, and this is only because of my feedback path. Now let's also discuss that what if when h of s is not equal to 1. It is pretty simple, by the way. However, let's discuss if h of s is not equal to 1. Then let me quickly draw system over here. There would be R of S, there would be a negative feedback, there would be a G of S, there would be Y of S, and here I have E of S, H of S, and this is over here. So in this case, my Y of S would be equal to G of S into EA of S. Putting the value of error signal over here, I will get G of S into R of S minus H of S into Y of S. Y of S is equal to G of S over 1 plus g into h of or g of s into h of s into r of s. So error signal over here would be equal to 1 over 1 plus g of s into h of s multiplied by r of s. So if I compare these A, B, C equations, I can see that I can see only by inspection that the equation C has the minimum value of the error because the denominator factor is the largest in all of these three equations. Here I have in equation A I have no denominator. In equation B the denominator is 1 over 1 plus gs where h of s was equal to 1. In equation C the denominator is 1 plus g of s into h of s, and it is the largest out of three equations, so it would the error in this case would be the lowest, and obviously that in order to reduce the error I have to reduce the 1 plus g of s into h of s term. I have to reduce this term to reduce the error signal, to reduce the error signal. So this was the first characteristic of the feedback control system, that we can reduce the error using our feedback path. We can visually see that error in case of feedback uh, is error is reduced when you have a feedback path. So this was the first characteristic of your feedback control system. Next is let's discuss sensitivity first. Sensitivity sensitivity of control system to parameter variations. Now, what is a sensitivity of control system to the parameter variations? It's just like that if you have a system, if you are giving some input and it is giving you some output, if there are some if there is some change in atmospheric conditions or or any conditions, if temperature changes, if humidity level raises, or if there is a noise, or if there is more disturbances in the system, and your if output is altered, or if output is changed, or if the output is affected, then you can say that your system is sensitive to these changes. If your system is performing well at 20 degrees centigrade and it doesn't perform equally well at 50 degrees centigrade, then you can say that your system is sensitive to temperature variations. Similarly, if you have a system and if it ages, for example, if it is a new system, its performance is good, and if after 5 to 10 years or 20 years, if its output changes, then obviously this system is sensitive to time, and this system is not robust but rather a sensitive system. So from this discussion we have an idea that a more sensitive system doesn't feel like a good thing to us, because system shouldn't be such a sensitive system. System should be a robust system. A system should be such that there is no change in output when there is disturbance, when there is some parameter variation, when you can say, for example, if you are receiving a signal on phone, and if there is rain or hailstorm outside and your reception is bad, then you can say that your system is sensitive and it doesn't perform equally well in different weather conditions. That system would be a compromised system. That system wouldn't be appreciated much, because its output will deteriorate with the effects in the parameters of your you can say g of s. If you have, so g of s is actually a system, or you can say g of s is a process. So if there is some disturbances, or if system is getting old, its g of s changes. If there is a disturbance, if it has an effect on g of s. G of s actually feed forward path gain, which we have discussed over here. This is the g of s. So whenever your g of s changes, uh, if your output has no effect on small change in g of s, then you can say that your system is not that much sensitive. However, if your temperature changes and g of s changes and subsequently your output is changed, then you can say that you have a sensitive system. So sensitive systems are obviously, you can say, discouraged. The feedback, whatever the system, if it is sensitive, the feedback loop basically reduces the sensitivity of the system, the dependence on change in g of s. So the feedback loop basically reduces the dependence of the system on g of s. For example, to explain this, I can write that y of s in a closed loop system that we have just written was g of s over 1 plus g of s into h of s into r of s. This is a typical equation of a feedback loop that you people already know. If uh, if I make g of s very greater than 1, then what will happen? Then let's write y of s. Y of s would be g of s divided by. Now if this g of s is very much greater than 1, then this 1 plus g of s h of s term can be written as g of s into h of s into r of s. So if you see, this g of s will be cancelled with this g of s, and your output would be only r of s divided by h of s. Isn't this interesting? That your output is no longer dependent on the g of s. Your system is not sensitive. Obviously this is not practically possible that your g of s is very much greater than equal to 1. However, you can see the property of a feedback system, that if you have a g of s sufficiently large, then obviously you can reduce the sensitivity of the system uh, to a smaller changes in the atmosphere. So obviously making g of s very much greater than equal to 1 is an expensive process, and it is equivalently to, for example, if you have a sound amplifier and you have you make its amplification factor very large, then obviously the small changes in the atmosphere or the noises of the people won't affect your system much. However, if your amplifier has a smaller gain, then obviously the noises, surrounding noises, would affect your system. Similarly, it if I make it if I make an analogy for it, I can say that the larger the system, the smaller the effect of disturbances, or the less sensitive it would be with respect to the disturbances. However, obviously the larger system has their own practical limitations, and it wouldn't be practically possible. However, just to see the property of a closed loop system, that the closed loop system can even eliminate on g of s itself. So whether whatever the change in g of s due to the parameter variations, it wouldn't affect your output. Now let's see few things mathematically, that if in open loop OL, I am writing an open loop system as OL. In open loop system, if I have a small rate of change, let's suppose your g of s is now changed to g of s plus delta g of s. Let's see how this change affects our open loop system and closed loop system. What have we done? We have introduced a small parameter variation in our g of s. We have changed our g of s to g of s plus delta g of s, and we want to see what this effect uh, would do with the open loop system and closed loop systems. In open loop system, obviously its effect will be proportional. It will have a direct effect on the output. So there will be a delta y of s, that is a change in output, that would be equal to delta g of s into r of s. Input multiply by the change in g of s would be the change in y of s. So this is kind of a direct relation. There was a g of s which when multiplied with the r of s was giving you y of s. Now there is a delta g of s which when multiplied with r of s gives you delta y of s. So your overall output would be y of s plus delta y of s. This would be your overall output in open loop gain. Sorry, in open loop system. In open loop system, you have introduced a change, a small rate of change, a delta for g of s. Your input was earlier. Your input was sorry. Input needs sorry. Earlier, your process transfer function was g of s, and your input was r of s. Then your output was r of s into g of s. Now your input is r of s, and your process transfer function is g of s plus delta g of s. So your output would be y of s, which was initial output, plus delta y of s, that is due to delta g of s. So delta g of s has proportionally or directly affected your output. The rate of change in delta g of s, the rate of change introduced in g of s has a direct impact on y of s, and it has introduced a rate of change or delta change in y of s. Let's now see that what will happen in a closed loop system due to this change in g of s, due to this small change in g of s. So it would be, let's say, y of s plus what would be this delta y of s for a closed loop system. That would be equal to g of s plus delta g of s over 1 plus g of s plus delta g of s into h of s multiplied by r of s. Just putting g of s plus delta g of s in the place of g of s in your this standard equation. So I have changed g of s to g of s plus delta g of s. So I am actually interested in delta y of s. So let's take this y of s on the other side. So my delta y of s would then become g of s plus delta g of s divided by 1 plus g of s plus delta g of s into h of s to r of s minus y of s. So I can write it as g of s plus delta g of s divided by 1 plus g of s plus delta g of s into r of s over h of s minus, let's put the value of y of s, which was initially g of s over 1 plus g of s into h of s into r of s. from here. So taking LCM, this would be 1 plus g of s plus delta g of s into h of s to 1 plus g h of s. I have this g of s multiplied by r of s would be this g of s r of s, and this g of s r of s would be cancelled. So in the numerator I will only have delta g of s. So I have the expression for delta y of s as delta g of s over 1 plus g into h of s whole square when g h of s is very much greater than delta g h of s. So this is the equation. When I put this g h of s is very much greater than delta g h of s, then obviously 1 plus this 1 plus g h of s and this 1 plus g h of s would make 1 plus g h of s square, and this term will be ignored or will be vanished due to its small size, as we already know that we have taken delta g of s as a small change in g of s. So if I assume that delta g into h of s is very small as compared to g into h of s, then this term can be ignored, and this overall your function is your delta y of s would be this. Now let's compare this equation. Let me call it as B1 with our open loop system. Let me call this equation as A1. So in A1, the rate of change in y of s was proportional. Means if you have a change in g of s, you directly have a change in y of s. However, in the closed loop system, when you have a change in g of s, the output change in output is delta g of s divided by 1 plus g h of s whole square times lesser. So the system is less sensitive by this amount, by 1 plus g h of s whole square. There is r of s as well over here, which I forgot to write. So when you compare this equation with this is delta y of s and this is y of s, this is delta y of s, sorry, r of s, and this is r of s. The here it is delta g of s and here it is delta g of s divided by 1 plus g h of s whole square. So the change in output is 1 plus g h of s square times less than change in output in open loop system. So you can say by feedback path or by a closed loop system, your system is more robust and your system is less sensitive to a change in g of s. So if you have a parameter change, if you have an atmospheric change, if you have a temperature change, and subsequently if you have a change in g of s, which is actually delta g of s, then your output will be changed by the amount that delta g of s divided by 1 plus g h of s whole square times. However, in open loop it was directly delta g of s times. So your output is less sensitive to change in g of s in your closed loop or your feedback system. So With this result in hand, let's formally define what your sensitivity of the system is. With this definition in hand, I can write that sensitivity of a system is equal to percentage change in system transfer function divided by the percentage change in process transfer function. System transfer function is the overall transfer function of the system, and the process transfer function is your G of S. So the percentage change in the overall transfer function of the system due to the change in the process transfer function, or the G of S, is called as the sensitivity of the system, or you can say that S is equal to delta T of S over T of S, when T is the overall transfer function of the system, divided by delta G of S over G of S. Now you can clearly see that in open loop, the process transfer function and system transfer function are same. So in open loop, the sensitivity value is 1. However, in closed loop system, the sensitivity value would be G of S over G over 1. You can calculate it as well, 1 over 1 plus G into H whole square, and you can have 1 over G of S into H of S. So sensitivity of a control system, you can put that, you can find the overall transfer function of a closed loop system, change it a bit, change it into a delta T of S, and then by calculating you will get the sensitivity of a closed loop system as 1 over G of S into H of S, which is obviously lesser than the sensitivity of an open loop system. So we can conclude that an open loop system is more sensitive and closed loop system is less sensitive to the parameter variations in your process or in your environment. So with this in hand, I can have a very brief discussion on some other characteristics of the feedback system. For example, control of the transient response, control of the transient response of the system, response of the closed loop system, and the controlling of the closed loop system is better than obviously the open loop system. Uh, at this point, I assume that you people know what is a transient response, the response to a very short change in input, or the response to the signal which is very short in the time duration. In order to control the open loop system, we have a controller in series, or a PID controller in series, or anything like that. We need to put it up in an open loop sequence to control the output of the system. For example, in a motor you have, let me give you an example of motor. In order to control the output of the motor, you either or fan, you can either install the dimmer can control the output of the fan. Whatever the input is applied to the system, it will directly result in the output of the system. So a controller or a dimmer or a resistor, anything can be installed in series, in a loop, in series. For example, it is a K can be a controller, this is your transfer function, and this is your output. So your open loop system can be controlled with this K. However, the problem is this, that we have no idea what the output currently is, because we have no feedback path, we have no way to sense the output. However, in closed loop system, we can measure the output. For example, in we can say that in a car we have a tachometer. Tachometer measure the current speed of the system. It will generate voltage which is then compared with the ideal voltage. If it differs, then obviously input is changed accordingly. The cruise control of a car works in a closed loop system. You already know what is open loop and closed loop. The control of the what we are talking in this article or under this topic is in what topology, either in open loop or closed loop, the control of a transient response of the system is better. So we can clearly establish that control of the transient response is better in a closed loop system rather than in an open loop system, because we have knowledge about the current output. We can compare that current output with the reference output, and then according to that error signal we can alter our input or alter our controller gain. That will result in your that will result in output becoming closer to the actual, thereby reducing the error. So after control of transient response, we can also see that the disturbance signal obviously is more absorbed in your feedback path. In your closed loop systems, we have just learned that the closed loop systems are less sensitive, and obviously the disturbances which come all along in the process can be absorbed or can be ignored, or they have less effect on the output of the system in case of closed loop system. um, okay, one thing, in order to check the effect of disturbance on some specific output, I already discussed by the way, but let's recap that if I want to check that what effect does this disturbance have in our system, then what is the procedure? For example, if you have an input and if you have some this block, some comparator, and this is the disturbance signal entering, and then some this block and then output. So we take this disturbance signal as a formal input. It is actually a single input, single output system. However, due to disturbance, it is now double input and single output system. So in order to calculate the effect of disturbance, we take this input or we make this input equal to 0, and we find the transfer function as y over d. This transfer function will give you the effect of disturbance on your system. Ideal transfer function would be the transfer function of the system would be y over input. If there would be no disturbance, then this would be transfer function. However, in case of disturbance, y over d is the transfer function with respect to the disturbance when no input is applied. When there is no input, then output will totally be because of that disturbance signal. So the overall output of the system would be this actual output of the system, the actual transfer function of the system, plus due to this this transfer function due to the disturbance on the system. So bottom line, if you want to find what effect your disturbance has on output individually, then you make your input equal to 0 and find a transfer function taking d as input. So that y over d will give you exactly the effect of your disturbance signal on your output. Okay, ji. Then we have another very interesting article, which is, let me use another ballpoint, another color for this. Let's use red. So this is a very important and interesting topic in control system. I think this topic is not in your book, so is not in Dorf. However, you can find this in your reference books. The reason why we are discussing this topic, because this holds a critical importance in control systems, and if you are planning to do MS or PhD, then the transformations obviously would have higher impact, and you need to know about these, and you need to have the basic knowledge about the similarity transformation. We will not go into the complex details, but we will discuss what we need to discuss. So, first of all, what is similarity transformation? Basically, we already know that a system has a system can have multiple state equations. A system has multiple state, you can say state variable models, having same transfer functions. For example, we studied when we started our discussion of state variables that system can have multiple sets of state variables which define the state of the system, because state variables are those variables which when combined with the input can give you the output. So there can be multiple sets of those state variables. uh, we studied, or we saw, that when there was a single transfer function could have multiple signal flow graphs, could have multiple state equations, yeah, or state variable set, or state variable models. So can we move from one state variable model to another state variable model? Why this is important? Because uh, this is all associated with linear algebra, and we want to have the forms which we assume, or which we can use for further calculations. We can change our state variables to some other state variables, so that the set we have taken is an ideal set, or it can help us to find e raised to the power at, or the state transition matrix, or some other variables easily. So similarity transformations, Jordan was the man who basically worked in this field. So we will briefly discuss what Jordan said as well. But obviously I will try to stay brief, and I will try to just give you the basic concepts of the similarity transformation, and the basic calculations, or the basic numerical type of this similarity transformations. Basically, you already know that each set of the system represents the same system. It represents the same transfer function, but state variable models would be different. We can transform from one set of state space equations to another set of state space equations without traversing through transfer function or the signal flow graph. For example, if we have, let's write it. If, for example, if we have x dot equal to ax plus bu and y equal to cx plus du, then we can have another set of state equations, which is z dot is equal to q inverse aq z plus q inverse b into u, and y is equal to cqx plus du. Here a is transformed into q inverse aq, b is transformed into q inverse b, c is transformed into cq, and d remains same. So this q inverse aq, q inverse b, cq and d gives you another set of state equations. Now what is this q? Q is basically you can say a basis, or actually it is a basis vector, but at the moment you don't know what is a basis vector. Q is basically a vector or a matrix. Q is basically a matrix having orthogonal, or you can say linearly independent vectors which can serve as a basis vector. Now I am sure you wouldn't be able to understand this sentence. Uh, Let me try to make it easy for you. What is Q? For example, if you have some vector this, if you have some vector this, and someone asks you to write this vector in terms of this and this. Let's say this is vector A, this is vector X, this is vector Y. Then you can say that U is equal to something into X plus something into Y. You have represented U in terms of X and Y, where X and Y are linearly independent vectors, and they represent the base. All the you can say all the vectors that can be made from this X and Y form the range space of vectors X and Y of this basis, of these basis vectors. We can, just like U, we can make multiple other vectors using X and Y. For example, if I have 1 0 and 0 1, there is a vector 1 0, there is a vector 0 1. These both are orthogonal vectors. We can make another vector by adding these two. 1 plus 0 1, 0 plus 1 1. This 1 1 is another vector which is the sum of these two vectors. So these two vectors are linearly independent, and this third vector is dependent on these two vectors. So these two are the bases, and this is in the range space of these two basis vectors. Similarly, we can make any other vector with the help of these two vectors. Just to refresh your concept, if I write this vector over here, then what is the rank of the system? Obviously here you have two rows, then you can see the rank of the system is 2. However, you can say if we have multiple rows and these two vectors are linearly independent, and this vector is made with the help of these two vectors, then your rank of this matrix is 2, because there are two linearly independent vectors, or there are two vectors which are orthogonal and which serves as a basis. And if there is, let's write another row. If there is a third row, then in this 3 by 3 matrix, you can say that there are two vectors which are linearly independent. So rank of your matrix is 2 and nullity is actually rank number of columns, rank minus, sorry, number of columns minus rank. Number of columns 3 and rank is 2. So here nullity is 1. Just to refresh your old concepts, this is not the part of obviously the topic, but however this knowledge would be important to understand the concepts, uh, to understand it more conveniently. So this is a very basic discussion that we can represent any vector in terms of its basis vectors. So if in this case, in this diagram, we can say that x and y serves as a basis vector and u can be defined in terms of this, in terms of this x and y. So this x and y in this case is q, this q, this q. So if someone asks me write Q for this system, I will write Q is equal to 1001 because this Q now serves as a basis, and from this Q I can make any other vector. So in this way we can transform one set of state variables into another set of state variable using this Q matrix. So that is why this Q matrix is important. Uh, Normally in undergrad, this Q matrix is given and you just need to multiply the matrices. That would be a simple matrix multiplication question, which obviously uh, I wouldn't wish that you people solve, because uh, having a solving something without having concept is I think is of no use. So you should know what are these things and why these are important. So this is Q. So once we have Q, you can see we can transform this x and y into z dot and y, or uh, this x dot into z dot, which is another set of variable, this x and y into z dot and y. So we can transform the system. One of the simplest, if I say one of the simplest example in which I don't need to calculate the Q matrix is, let's suppose you are given with the system x dot is equal to 0 1 0 0 0 1 minus 2 -5 -7. This is matrix A. This is matrix X. I am writing it in bold because it is a vector, is equal to 0 1 0 0 1 U. This is AX plus BU, and you have Y equal to CX plus 0 U. D is equal to 0 in this case. Now you are asked to transform it into a new set of variables where new variables are related to x as follows. Z1 is equal to, their relation is given, is equal to 2x1, Z2 is equal to 3x1 plus 2x2, and Z3 is equal to x1 plus 4x2 plus 5x3. That is in matrix form. I can write it as Z is equal to 2 0 0 3 2 0 1 4 5 into x. This matrix is actually Q inverse. So from here you can find Q, and from Q obviously you can calculate Q inverse AQ, Q inverse B, CQ and D. let me write answers, and you people, all of you should calculate all Q inverse AQ, Q inverse B, CQ and D for this specific example. Your Q inverse AQ would be, I am writing answer. Your Q inverse AQ would be minus 1.510 minus 1.25 0.7 0.4 minus 2.5 0.4 minus 6.2. This would be your Q inverse AQ, and Q inverse B would be 0.005, and CQ would be 0.500. So the new transformed system would be Z dot is equal to that A. This is now new A. I am writing is A prime AX plus B prime U. This is B prime and this is C prime. So go and see if your A prime, B prime, C prime have these values. You can use calculator as well, by the way. Uh, Now what I would like to do is to do a question where we need to find Q as well. Let me take a very simple question because I need to, what example should I take? Let's take A is equal, actually I need to take A which has distinct eigenvalues. So let's take A is equal to 0, 1, minus 2, minus 3. What are its eigenvalues? Eigenvalues are, by the way, the determinant of Si minus A. So it means what is Si? S00S minus what is A? 0, 1, minus 2, minus 3 is equal to S minus 0 S, S minus 1 minus 1, 0 plus 2 and S plus 3. Now take its, this is Si minus A. Now when I take its determinant, Si minus A determinant is equal to S into S plus 3 minus 1 into 2 is equal to S square plus 3S plus 2. I can write it as A square plus 2S plus S plus 2, S common, S plus 2 plus 1 common, S plus 2 is equal to S plus 1 and S plus 2. So eigenvalues are S is equal to minus 1 and S is equal to minus 2. So yes, eigenvalues are distinct. They can be complex as well. You can also have S is equal to 2 plus J or 2 minus J as far as they are distinct. So here I have two distinct eigenvalues. One is minus 1 and one is minus 2. Now I want to find our matrix Q. So as this is a 2 by 2 matrix and uh, I have a system with two eigenvalues, so I should know that my Q matrix would be in the form of Q11, Q12, Q21, Q22. I can write it as there it is composed of two vectors, vector q1, which is q11, q21, and a vector q2, which is q12 and q22. So I need to find these two vectors q12, q22 in order to find my q matrix. Just like this, these were two vectors. So these two vectors made this q. Similarly, these two vectors would make this q. Now let's find q1 and q2 with the help of eigenvalues. So there I have two eigenvalues. For first eigenvalue, which is s is equal to -1, let me calculate q1. The process for calculating is si minus a into q1 equal to 0. That is, I have already calculated si minus a, which is s minus 1 to s plus 3. If I put s is equal to -1 in this, s is equal to -1 in this matrix, I have -1, -1, 2, and -1 plus 3, which is equal to 2. So -1, -1, 2, 2. Let's write it as -1, -1, 2, 2 into q1 equal to 0. It would be better, or it would be convenient if we convert it into row reduced echelon form. In row reduced echelon form, I can see that this multiplied by 2 minus plus this would result this row equal to 0. So it would be then -1, 0, 0 by simply by row operation. Multiplying this with 2 and adding in row 2. Multiplying row 1 with 2 and adding with in row 2. I have got this in row reduced echelon form. Let's write q11 and q1 matrix also in the form of q11 and q21 is equal to 0. Expanding it will give me minus q11 minus q21 is equal to 0, implies q11 is equal to q21. If I say that my q11 is alpha, then q21 is alpha, then q11 would be minus alpha. So my q1 vector would be minus alpha and plus alpha. I can also assume these values rather than putting it alpha. I can also say that if q21 is 1, then q11 would be minus 1. Then I will write minus 1 and 1 as my q1. I can also write it that, but let's not lose the generality of the system, and let's try to derive something which gives us the conceptual conclusion. And similarly for s is equal to, for second eigenvalue, which is s is equal to -2, we have si minus a into q1. Putting s is equal to -2 in this, we have -2, -1, 2, and this -2 plus 3, which is equal to 1. So I have -2, -1, 2, 1 into q2 is equal to 0. Similarly, converting it into the row reduced echelon form, simply adding it into the row 2, I will have by row operation. So -2, -1, 0, 0 into q12, q22 is equal to 0. So from here I have -2 q12 minus q22 is equal to 0. That is q12 is equal to minus q22 divided by 2. So if I say that my Q12 is beta, uh, then is minus beta or beta, that is anything you like, then Q2 vector is minus beta and 2 beta. If Q22, sorry, if this Q12, if Q12 is beta, if Q12 is beta, then Q22 would be minus Q22 would be 2 Q12 divided by minus 1, or you can obviously take minus on this side as well. So Q1 is minus alpha and Q2 is minus beta and 2 beta. So again, if I take Q1 to 1 or 0, we can obviously have a numeric value for this Q2 as well. But one thing we should keep in mind while choosing the values is that this Q11 and Q22 should be linearly independent to each other. So, oh, I think I am short of pages. Oh, let me add page into this. Sorry for this. So let's resume. So this Q1 and Q2 we have established, so we can say that we have now this Q matrix is equal to minus alpha minus beta and 2 beta. Now this is our Q matrix. So similarly we have Q inverse is equal to adjoint of Q over Q determinant, which is actually adjoint. We can change the places of these two and change the sign of these two. So it would be adjoint of Q would be 2 beta minus alpha and beta minus alpha into determinant. What is the determinant? Minus 2 alpha beta plus alpha beta, which would be minus alpha beta. Minus alpha beta. So this would be Q inverse. So let's see what our A prime would be. A prime is actually Q inverse AQ, which is Q inverse AQ is 1 over minus alpha beta and 2 beta minus alpha. This is Q inverse. And what is our A? Our A is 0, 1, minus 2, minus 3. 0, 1, minus 2, minus 3. And this is Q minus alpha minus beta alpha and 2 beta. This is Q inverse AQ, which is our A prime. Let's solve it. 1 over minus alpha beta and 2 beta multiplied by 0. 0 plus beta into minus 2 minus 2 beta. Similarly, I can write 2 beta minus 3 beta, and here I have 2 alpha, and here I have minus alpha plus 3 alpha, and minus alpha minus beta alpha alpha and 2 beta. Then multiplying this with I have 2 alpha beta plus 2 alpha beta minus 3 alpha beta, and here I have 2 beta square plus 4 beta square minus 6 beta square, and here I have minus 2 alpha square plus 2 alpha square, and here I have minus 2 alpha beta minus 2 alpha beta plus 6 alpha beta. So minus 2 alpha square minus 2 alpha square, here I have 0. 4 beta square plus beta square, this is 6 beta square minus 6 beta square, sorry, this is 2 beta square plus 4 beta square minus 6, so this is also 0. So these two terms are 0, and this is 2 alpha beta 4 alpha beta minus 3 alpha beta is equal to alpha beta. Similarly 6 minus 2 minus 2, 6 minus 4 2. So I have a prime is equal to 1 over minus alpha beta into 0 0, and here I have alpha beta, and here I have 2 alpha beta. So this is by dividing inner terms with minus alpha beta, I have minus 1 0 0 minus 2 as an a prime. Now this is not just a result. I want to discuss something about it. This is a Jordan block. Jordan block. How? What were the eigenvalues? Eigenvalues were minus 1 and minus 2. Can you see the eigenvalues over here? Diagonally. Yes. So a Jordan said that if you have distinct eigenvalues, then your A prime is just write those eigenvalues in diagonal with zeros on the other side. So block diagonal it would be. So you can directly find A prime using Jordan block. So there was no need of doing all this calculation. If you are given with A, you know eigenvalues are minus 1 and minus 2, just directly write A prime as minus 1 minus 2 0 0. Whatever the eigenvalues are, if they are distinct, you can easily write A prime as I have written, as we have calculated A prime over here. However, if your eigenvalues are repeated, for example, if there was s plus 1 square, then you have minus 1 and minus 1. You have two eigenvalues, both are minus 1. If your eigenvalues are repeated, then there can be more than one Jordan blocks for single eigenvalue. For example, for example, for this block, let's suppose uh, if there was uh, if there were two eigenvalues minus 1 and minus 1, then the above, what would happen to the above Jordan block? For example, this is minus 1 and this is minus 1. This would be 0. Now what would be over here? If it is you can say that if it has a full row rank or full column rank, or you can say if its nullity is 1, then there is 1 over here. If nullity is 1, then there is 1 over here, and this complete is one Jordan block. If its nullity is 2, or then it will be 0 over here, and there will be two Jordan blocks, one this and one this, because this is repeated. In case of distinct, this complete was one Jordan block. In case of repeated roots, this one item comprises of one Jordan block and this is another Jordan block. If there was one over here, then this complete would have been a single Jordan block. So Jordan blocks help us to find, you can say, the transformation matrices, the A prime, directly just by inspecting the eigenvalues. If eigenvalues are distinct, it is very easy to write A prime because just write it in the diagonals. However, if eigenvalues are repeated, then you have to see the nullity of the system, and then you will derive how many Jordan blocks would be there. So if nullity is 1, then there would be one Jordan block. If nullity is 2, then there would be two Jordan blocks. So I think we should conclude over here. In case of any queries, you can write me on rafe.chughtai@uet.edu.pk. This is all from my side for today, and I think we have discussed a few of the most important concepts of the control systems. In case of any query, you can write me on this email ID. Thank you very much for your time.